Okay, in this video we're going to do some projectile motion problems where the projectile is being launched at an angle. Let's start with this one. You throw a rock off a bridge. The initial velocity of the rock is 8 meters a second at an angle of 53 degrees above the horizontal. It takes 12 seconds for the rock to hit the water below the bridge. Okay, before we get to the different things this question is asking, let's just draw a really quick picture. We have the rock being thrown into water, and I know that there's some initial velocity, which we can call v naught at an angle theta above the horizontal. Means if I draw a horizontal line, it's going above it. And then the trajectory of this rock is going to be a parabola that goes something like this. Okay, great. Before I even begin to look at A, B, C, and D, I know that I have an initial velocity v naught of 8 and an angle of 53 degrees. So what I'm going to do right away is I'm going to calculate the x and the y components of the initial velocity. And then to make it easier on myself, I'm going to write them as a vector in I for my x component of velocity and j for my y component, or like my upward component of velocity. So for y naught, I would do v naught sine of the angle, we'll just write sine theta, which is 8 meters a second times sine of 53 degrees. And 8 sine of 53 is 6.38, so we'll call that 6.4 meters a second. And then Vx naught, which since the initial x velocity is going to be constant, it's not going to change. You could just call this Vx. I like to do that. Then you would find this by doing v naught cosine theta, which is 8 meters a second, times cosine of 53 degrees. And that is going to give you 8 cosine of 53, 4.8 meters a second. So what I'm going to do is I'm going to store this in ij notation for my initial velocity, and I'll write 4.8 I plus 6.4 j. Then I can get rid of all this work. And if you're getting really good at these problems, you can just go ahead and do the 4.8 and the 6.4 in your calculator, and just go ahead and write this out for yourself so that it's there. You can, quickly solve the problem. 4.8 is the x velocity and 6.4 is the y. Okay, so for part A, how far from the base of the bridge does the rock land? That is asking you to set the initial x position to 0 and find the final x position. So to do this, I need the x velocity and I need time. And it does give me time. It tells me that the rock hits the water in 12 seconds. So this problem for part A is as easy as taking your x equation. This is the only x equation that you have because it's constant velocity. And plugging and chugging. So let's plug and chug. Our x velocity is 4.8. That's what we found. Our time is 12 seconds, and our initial position is 0. So 4.8 times 12 is going to give me 57.6 meters. Boom. That was really easy. Okay, so part A, done. 57.6 meters. Okay, well, let's do part B. How high is the bridge? Okay, so this is asking you to set the final y position to 0, or the final height to 0 at the water, and then work backwards to figure out what the initial position is. Okay, so what I would do here is I would take advantage of the fact that I have y naught, y, t, and vy naught, the initial velocity, and use the height equation that involves all of those variables. And there's not much rearranging that needs to be done for this. You really just need to plug in your time in your vy naught of 6.4 and try and solve for y naught. What I would do is I would rearrange this equation first and get rid of anything that's 0. So this is 0. And what I would do is I would just take these two terms and bring them over to the left side. So when I do that, it would actually be 1/2 gt squared. So you add that to both sides and then subtract vy naught t. And so that would equal y naught. And now I have a nice linear equation to plug my stuff into. Half of 9.8 meters per second squared times 12 seconds squared minus 6.4 meters a second times 12 seconds. This is going to give you an initial height of 628.8 meters, which is a very, very, very tall bridge. Okay, great. So that's how high the bridge is, 628.8 meters. Now let's work on part C. What is the maximum height that the rock reaches? Well, now that I have the initial height, I think I would probably graph this problem to figure out what the maximum height that the rock reaches. So what I would do is I would take this same equation that we just used, and I would write a graphable form of the equation. So this would be negative 4.9 t squared plus 6.4 t plus 628.8. Sorry, no units for the graphable, for my graphable equation. Okay, so then what I'm going to do is I'm going to graph this equation, and I'm going to get a sad face parabola that represents the height, and what I'm going to do is look for this maximum right here, because that will give me the maximum height that the rock reaches. So let's do that. Bring out our handy dandy calculator. Okay, and then we're going to go ahead and do y equals negative 4.9 x squared, x for time, plus 6.4 x plus 628.8. Okay, then I'm going to graph it. I know my scale, my window is going to be way off. Yeah, so we can try a couple of things. Why don't we do zoom 0, which zoom 0 is going to give us an attempt at fitting it, although it's going to be terrible. I know it's going to be terrible. Oh. That's not so great. Maybe I'll change my window a little bit. I'm not interested in too much of that x max. Maybe just do -1. That's like -1 second. And we can go up to 12 seconds, right? So it's 13. The minimum, the y minimum, we definitely want that to be like -1. Okay, and let's do a height of, let's say 650. Maybe that'll make it easier to graph. Oh yeah, wow, what a throw. Okay, so it's kind of hard to see this maximum. What I'm going to do is zoom, second calc, not zoom. And I'm going to go to maximum. I'm going to go very, very, very far to the left. Enter. And then go very far to the right. And this tells me that I reach a maximum of 630.8, so 639. So I would mark that here, 630. Wait, is that what it was? 630.9. And then I would mark the time at 0.65 seconds. Okay, great. So 630.9 meters. Great. Now, solving for how fast the rock goes before it hits the water, I know that the x component of velocity is still going to be the same. Okay, so that vx component is still going to be 4.8. And the y component is going to change according to the equation vy equals negative gt plus vy naught. So what I'm going to be doing here is basically trying to figure out what that y component at 12 seconds is. So we can say vy at 12 seconds is equal to negative 9.8 meters a second squared times 12 seconds plus are 6.4 meters a second. Okay, so this is going to give me negative 9.8 times 12 is negative 117.6 plus 6.4, negative 100, wow, 0.2 meters per second. This is a very tall bridge. Okay, so that's the y component, which means it's very, 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 very long. That's your y component at 12 seconds. So if I wanted to write this in vector notation, maybe that would be helpful. I'd write v12 equals, so again, the x component doesn't change, so 4.8i minus 111.2j. Now, to find the magnitude, which would be the diagonal of this little parallelogram, I would do the square root of 4.8 meters a second, the whole thing squared, plus negative 111.2 meters per second, the whole thing squared, and that is going to give me a big number that's very close to 111, probably. Yes. 111.3. Okay, let's do another problem. You chuck a pumpkin, giving it a velocity of 22 meters a second at an angle of 30 degrees above the horizontal. The pumpkin hits a brick wall 25 meters away. At what height did the pumpkin hit the wall? Okay, so again, we're just going to set this problem up. I'm going to go ahead and draw, let's see, little pumpkin. Perfect. And we'll give it like a, there we go. Okay. At an initial velocity, some angle theta, it says above the horizontal, so I'll just draw a little horizontal line, and I know theta goes above it. And right away, since it gives me the magnitude and the direction of this velocity, what I'm going to do is I'm going to go ahead and write my initial velocity as an ij vector. Okay, so 22 cosine of 30 is my x velocity, and that's going to be constant. Then 22 sine 30 is my y velocity, or my upward velocity. Oh, sorry, 22 sine 30, which is 11. So 19.05, we'll call that 19.1 is my x velocity, and 11 is my y. So 19.1 I plus 11j. Those are the x and the y coordinates of my initial velocity. Okay, then I'm going to trace this trajectory. And the pumpkin hits the wall and splatters, and it's awesome, and everybody's excited. And I call my mom, and I'm like, but the pumpkin hit the wall, and she's all excited. And I know that this happens 25 meters away. So this means I'm going to set my initial x to 0, and then my final x at 25 meters. Now, the goal of this problem, then, is to figure out if my initial height is 0, we're going to assume this pumpkin was chucked at 0, then what is the final height that it reaches at that 25 meters where it splats? That's what the problem is asking me to find. Okay, so maybe you see that right away you have enough information with the x velocity and the x positions to solve for the time that the pumpkin is in the air. Always a useful thing. So we're going to use our equation. X equals vxt plus x naught. Our initial x position is 0, so we can just get rid of it. And then to solve for time, I'm just going to divide both sides by the x velocity. So time is equal to x divided by vx, which is 25 meters, that's the x, divided by 19. Let me rewrite that. 19.1 meters per second. Okay, so that is going to give me 1.3 seconds. So now I know the pumpkin is in the air for 1.3 seconds. That's useful to me because I can use that time and these heights and the initial y velocity to solve the equation that we've been using for a lot of these problems. So the vertical position equation. Why not? Okay, finding the height is as simple as just plugging in numbers and chugging away. So the initial height is 0, we get rid of it, and negative 1/2, 4.9 meters per second squared. I'm sorry, negative 9.8, half of 9.8 is 4.9, times the time, so 1.3 seconds squared, plus your y initial velocity is 11 meters a second times 1.3 seconds. Okay, so this is going to give you 6.171, so we'll say 6.2 meters. So that is the height above the ground, or above where the pumpkin was launched, that the pumpkin hit the wall. Great job. Let's do one more problem together. You are programming a robot to shoot basketballs at a regulation height hoop, which is about 3 meters tall. The robot has a set initial velocity of 15 meters a second at an angle of 37 degrees. How far from the basket does the robot need to make the shots? Okay, so we're again going to assume that this robot is shooting the basketballs from the ground. Maybe it's got some sort of like lacrosse stick that it's granny shotting with. I don't know. But here's the basketball on the ground. Sketch it. V naught. Angle is above the ground, so it's going to look like that. It's a terrible arrow. And the trajectory is going to look something like this. Right, here's my basketball hoop. It's fantastic. Oh, wow, you love drawing basketball hoops. Yay. Okay. We are trying to figure out if the initial x position is 0, what will the final x position be? Like, how far away should this projectile be launched from? Now, already I know the initial height. We'll set that to 0, and the final height is 3. And I know that I should take this initial velocity and angle and get an x and a y component for myself. So get my calculator, and I've got 15 and 37 degrees. So 15 cosine of 37 is 11.97. We'll call that 12. And then 15 sine of 37 is, we'll call that 9. So 12 and 9. 12x, or 12i, sorry, plus 9j. So those are the x and the y components of my initial velocity. Now, if I want to figure out how far forward it goes, then I'm going to need to figure out at what time it reaches the basketball hoop. And I can use this equation that we've been using quite a bit to write a graphable equation for myself. So if I was going to write a graphable equation, I would do this. Half of 9.8 is negative 4.9, so negative 4.9 t squared, plus the initial y component of velocity is 9, so plus 9t, and then my initial height is 0, so I would leave that as 0. I could set this equal to 3, which is the height, and then solve for time. But that is going to require me to use the quadratic equation and take just a little bit more algebra time. Instead, I'm just going to straight up graph this equation. And if I get my calculator out, I go to y equals, and I graph this, so negative 4.9 x squared plus 9x, and I graph it. Let's see, this is terrible, so our window is not, oh my god, well, this is from the bridge problem. Our y max, well, the height of the hoop is 3, so let's say like 5. And the maximum time, I bet it's not very long. Let's say 5 seconds. Oh, perfect. That's great. Okay. So here's what I can do. If I want to figure out what times give me a value of 3, then what I'm going to do is go to y equals and graph a separate line at 3. Now I have two intersections for my height function, where I can decide that the basketball is at a height of 3. Now, here's the thing. There are two answers for time. If I pick this first time, then that means that the basketball is on the way up, and it's going to hit the hoop, but hit the hoop on the way up. Now, if this was just straight up like you just want to hit a target, then you would choose that first value of time right there. But since you want this basketball to go into a basket, then you're going to want to select this second answer for t, for time, because that's when the ball is on its way down. And you want to time it so that while it's on its way down, it hits that height of 3. So to figure out this time, I'm going to go to second, calc, intersect. I'm going to find this second intersection. Oh, where'd the first curve go? There we go. Okay. So to the left of the intersection I want, then to the right, then I press enter, and boom. At 1.39, so 1.4 seconds. That's the answer I want. At 1.4 seconds, the ball will be on the way down and at 3 meters. So I use that 1.4 seconds to work out my equation for x and figure out how far away it needs to be. So my initial position is 0. I get rid of that. My x velocity is 12. So 12 meters a second times 1.4 seconds is going to give me 16.8 meters. So that's how far away this robot needs to be so that it makes a swish. Congratulations, this video is done.